Okay, we're going to take up what are seemingly two unrelated items, and pretty much they are. I'm getting to the point in our school year where um, we have to tackle kind of like leftovers, if that makes sense. So it's like there's three small topics, two lessons of material that we haven't covered yet that are kind of like they don't fit neatly anywhere else. So the first one is that there is a mean value theorem that is in an integral form. So we've seen the mean value theorem where at some point the slope of a continuous function at a point has to be equal to the average value of that function. So if we take the slope has to be equal to the derivative. The slope of the secant line, there we go. The slope of the secant line has to be equal to the derivative at some point. There we go. That's the mean value theorem for derivatives. Now let's get a mean value theorem for integrals. Okay, so the theorem says this: if f is, again, continuous on closed interval AB, right, then there has to exist C, which is also on closed interval AB, such that f of C is equal to the average value of the function. So 1 over b minus a times the integral from a to b of f of x dx. So what we're saying here is that there has to be some point along the continuous function where the value of the function is equal to its average value. Okay, this can also sometimes be written as the integral from a to b of f of x dx has to equal f of c times b minus a. These are equivalent statements. Okay, so let's take a look at what that means geometrically. So the geometry of this is actually quite simple. You literally just draw the curve f of x. Oops, let's make this a little more steep. Let's say f of x goes like this. There's f of x. There has to be some average value of this function between a and b. Let's say that average value happens here, which means there has to be some point C between A and B where that average value occurs. That's all we're saying, is that there has to be a point where the average value occurs at C, and we're good. I'm going to prove this real quick because the proof is actually quite simple, and it shows you that this is really just a restatement of the mean value theorem for derivatives using an integral. So let's take a look at how that works. Okay, so let's let big F of x be the integral function from a to x of f of t dt. So this is the integral function. By the mean value theorem for derivatives, we get that there exists some c on the interval AB such that the derivative of big F at C is equal to big F of B minus big F of A over B minus A. Now, given that we started our integral function at A, we can say that f of A is equal to the integral from a to a of f of t dt, which is 0, because this is an integral that goes nowhere. Okay, so this is an important fact we're going to use in a minute. By the fundamental theorem of calculus, we get that big F prime of C is little f of C, right? So the fundamental theorem of calculus, I get the big F prime of C is the same as little f of C, because we have it that big F of F prime has to be the antiderivative of F. So if you take the derivative of big F, we get little f, right? That's FTC. So let's combine this together. I have little f of C here has to equal big F prime of C here, which is also here, has to equal big F of B, and this is just 0, so that goes away, over B minus A, but big F of B is going to be the integral from A to B of f of t dt, and we've proven it. There it is. I've got little f of C is equal to 1 over B minus A of the integral from A to B of f of t dt. I'm good. I mean, you can replace the t's here with x's if you want to. It doesn't matter. It's there. All right, so let's do some example work here. So let's say we want to find the value that satisfies the mean value theorem on f of x is 1 plus x squared over the interval -1, 2. So we want to find the c that makes this statement of integration true. So we want f of c to be the integral, to be 1 over 2 minus -1 times the integral from -1 to 2 of 1 plus x squared dx, right? So this tells me that I want 1 plus c squared to equal 1/3 the integral from -1 to 2 of 1 plus x squared dx, right? Okay, so let's simplify a little bit here. I'm going to bring the 3 over. That's going to give me 3 plus 3c squared is equal to, let's see, that's going to give me x plus 1/3 x cubed from -1 to 2. So this is 3 plus 3c squared is 2 plus 1/3 times 8 minus -1 minus 1/3. This gives me 3 plus 3c squared is, let's see, 2 minus -1 is 3. 8/3 plus 1/3 is 9/3. That's also 3. So that's 6. Okay, so let's subtract 3 from both sides. We had 3c squared is 3, which means that c squared is 1, which means c is plus or minus 1. And both of these are on the closed interval, so either one of these satisfies the conditions of the mean value theorem for integrals. So there we go. There's your MVT for integrals. So that's one of 2 concepts that we wanted to take in this video, which is kind of like leftover stuff. The other one is completely unrelated, other than the fact that it uses an integral, so it's an application of an integral. So let's take a look at that. Okay, so we had to leave one last convergence test to the end here because we didn't have an integral yet. Okay, so there is one other way that we know easily to prove convergence of a series. So we're back in a series land, just for a short little trip here. So we have this thing called the integral test. What the integral test says that there exists some n, which is a positive integer, such that if f is continuous, positive, and decreasing. So that's a lot of things you have to meet. It has to be continuous, positive, and decreasing on the interval from big N to infinity. And on that same interval, a sub n is equal to f of n for all n equaling 1 out to infinity. Then the series n equals 1 to infinity of a sub n converges if and only if, so this goes both ways, the integral from big N to infinity of f of x dx is finite. So it has to be finite. So it has to be less than infinity. Another way of viewing this is that it converges itself. The integral converges if it's finite. So this is how we could look at this. So let's look at an example where we get convergence here, and then we'll look at also an example where we might get some semblance of divergence. Okay, so let's take the example of the series from n equals 1 to infinity of 1 over n squared plus 1. So we're going to let f of x be the related function, 1 over x squared plus 1. Now, I want to look at this because, see, we have to check this on the interval from 1 to infinity. And lo and behold, on that interval, this is continuous. It is decreasing. And it is positive on that entire interval. You can double check that. That works. So I am now subject to the integral test. So let's take the integral from 1 to infinity of 1 over x squared plus 1 dx, right? All right, so this is an improper integral, so I have to take the limit as b approaches infinity of 1 to, of the integral from 1 to b of 1 over x squared plus 1 dx. Okay, so that integral happens to be the inverse tangent. So this is the limit as b approaches infinity of the inverse tangent of x from 1 to b, which is, well, this is the limit as b approaches infinity of the inverse tangent of b minus the inverse tangent of 1, right? So the inverse tangent as we're going to infinity is pi over 2. The inverse tangent at 1 is pi over 4. And if I take pi over 2 and subtract pi over 4, I get pi over 4, which is definitely not infinity. Which this means that the series from n equals 1 to infinity of 1 over n squared plus 1 converges. So there I used an integral to prove the convergence of an infinite series. Now, this series also is like comparable to a p series where p equals 2. It has to be, it's dominated by that. The p series converges, therefore by the comparison test this also converges. I'm not suggesting that the integral test is the easiest test to grab for, but it definitely will do the job in certain circumstances. Okay, so let's look at the next example here. All right, so we did a really long roundabout way of proving that the harmonic series diverges. Here's another quick proof of it using the integral test. All right, so we're going to give this the related function, which is 1 over x. Note this thing is continuous on 1 to infinity. It's not continuous at 0, but it's continuous on 1 to infinity. It is positive on that interval, and it is decreasing. So we have met the conditions of the integral test. So let's take the integral from 1 to infinity of 1 over x dx, which is the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. This is the natural log of the absolute value of x. Well, there's a limit in here still, right? Limit is b approaches infinity, the natural log of absolute value of x from 1 to b. So this is going to give me the limit as b approaches infinity of the natural log of b minus the natural log of 1. But the natural log of 1 is 0, but the natural log going to infinity is going off to infinity. So, because the integral test is if and only if, this means that if this is going off to infinity, this means that the series has to diverge. Okay, again, not the easiest test in the world. Normally on the AP exam, you just say that the harmonic diverges because it's the harmonic. But here is another proof that the harmonic diverges. All right, so 2 out of 3 last kind of unrelated things for the year. The mean value theorem for integrals and the integral test for series convergence. And next video, we get the last one, which is on logistic growth, and then we have completed the BC content for the year. Awesome.